This is Decay here with today's lesson on exponential growth and decay, as well as how to graph these exponential functions. So what we're going to take a look at first is when we have a certain amount of something and it's growing over time or increasing, something you might see later as well as increasing interest or inflation, the growth of bacteria, or most populations grow exponentially. So we're going to take a look at how we can calculate over any period of time these growths. So let's say for something that costs $30 and we want to find out how much it costs in one certain period of time. So if it grows by 5%, the way we convert our percentages to decimals is by moving it over 2 places. I've got 2 other easier examples up here that you can also reference for the future if necessary. So this would be able to tell me in 1 year's time with a 5% growth rate what my total would be. So something that costs $30 initially will cost about $31.50 in 1 year's time. But let's say we wanted to go ahead and calculate it 2 years down the road. Well, we just add that growth rate, 1.05. Keep in mind that anything that is greater than 1 here will be a growth, and if it's less than 1, it's that decay that we'll talk about later. So this would give me my new total of about $33, what something would cost 2 years down the road that initially cost $30 with a 5% growth rate. So now if we look at it a little bit further, we've got 30, and now we just write this 3 times. So is there an easier way to write 1.05 times 1.05 times 1.05? Yeah, of course. Instead of just rewriting the same thing, you can actually use your exponents. So if we wanted to now calculate something to 5 years down the road, we'll just start with something a lot simpler, and we put it to that 5th power. So that will allow us to calculate not only the first 5, but 10, 20, 50, 100 years down the road, what something might cost or what something might grow to if it were one of my other examples here. So we're going to go ahead and take a look at this table. So it started at $30, and 5 years down the road, it might cost closer to $40. So another important factor when it comes to exponential functions is the slope is increasing. As you progress through the x values, the difference between each one changes. So the difference between 0 and 1 is just 75. But when you look over here between 4 and 5, just a few later, it's almost 3 times that at 214. So that means the slope is increasing, which is one of the characteristics of exponential functions. I've got a quick graph up here. You can see how it curves in contrast to our linear graph that's just a straight line or a diagonal line. So the next thing we're going to go and take a look at is exponential decay. So if I have it way over here, decay would be something like your half-life you learn in chemistry. Let's say we've got a radioactive isotope in the amount of 200 grams. Half of it's going to disappear in a certain amount of time. So if we go ahead and calculate that, like I mentioned earlier, our decay, that number is going to be less than 1 because it's referring to the fact that our initial substance is getting smaller. So now we have our 200 and we multiply it by 1 minus 0.5. So that's how we get a number less than 1, because instead of adding for growth, we're taking away for decay. So same thing if we wanted to go ahead and calculate that for 50 years down the road, we would just raise it to that particular exponent and go ahead and calculate. And then the difference between a growth function graph, where it goes up, the decay would just be reflected. It pretty much is going to get ever closer to y is equal to 0. But there's a horizontal asymptote, so it won't actually reach it. It'll just get very, very close as x approaches infinity. All right? Thank you for paying attention today. Remember to like, comment, and subscribe.